Okay, I want to tell you about elliptical orbits and how the conservation of energy applies to elliptical orbits. Okay, so we have an elliptical orbit here. Um, this would be maybe the sun, and then maybe one of the planets, and these are two different positions that it will find itself in as it orbits. Now, as we said before, with Kepler's laws of planetary motion, the closer it is, then the faster it goes. So what happens is, I'll trace this out. So what happens is this thing starts out here, it's going slow, gains more and more speed, and it whips around, and then it slows up, and then it gains more and more speed, and then it whips around, and then does that. It's almost like it's falling into the planet but missing it. So as it falls into the planet, it gains more and more speed, but then it whips around, and then it's almost like it's shooting up away from the planet, which means it's going to lose some speed. Now, how does energy factor into this? Well, we're going to just say that the energy here at position A is equal to the energy at position B. Now at A, it's got a velocity A. This is a velocity A, and this is a radius r sub A. And then this will be a velocity VB, and that's a radius r sub B. And so this is how you do a problem like this with energy. If you want to know, if you know all this stuff, say, but maybe you don't know VB, but you know this, and this, how do you get VB? Well, you just apply the conservation of energy. So you say E equals E prime, or in other words, the E at A equals the E at B. And so what is the E at A? Well, it's got two types of energy at A. It's got kinetic energy there. So it's got 1/2 mass of the planet times the velocity at A squared plus, now it's also got some potential energy, and this is where we're going to use the potential energy formula that we learned at the beginning of the year. I'm not going to say MGH because I don't know G there, and what I really need is the absolute gravitational potential energy there. So that's going to be negative G times the mass of A, or the mass of the planet, times the mass of the sun, all over the distance between the two, not squared. So that's that equation. I'll be deriving this equation for you in another video, maybe a week or so down the road. So this is 1/2 ma squared plus negative gmms divided by Ra. This is the kinetic energy. This is the potential energy, the gravitational potential energy. Hey, that equals, if you come around here, that should equal the kinetic energy at B plus the potential energy at B. Again, don't square these. They're not squared. And remember, they are negative. These are negative potential energies. And so you see that every term has a mass of the satellite or the mass of the planet in it. So I'm going to go ahead and get rid of these. And then if you need to solve for, say, the velocity of B, maybe you bring this term over to the other side. And well, let's do that. Let's say I'm solving for VB. I'm just going to bring this term on to the other side. So 1/2 ma. And when this term goes on the other side, it's going to be a positive. So I'm going to say plus G mass of the sun over RB minus G mass of the sun over RA is equal to 1/2 VB squared. Let's multiply every term by 2. and then we can combine terms. So apparently VB is going to equal, I'm going to take the square root when I get done, but it's going to be equal to, this is VA. VA. It's VA and it's squared. Gee whiz. Okay, so this is going to be VA squared plus, and maybe I'll pull this GMS out of there and just do 1 over RB minus 1 over RA. And then I'll take the square root. Okay, one more time. Do you want to memorize all this? No, you're not going to memorize this. You can just start out with E equals E prime, and then you've already memorized 1/2 mv squared and negative G m1 m2 over R. So you just apply it, and depending on what you want to solve for, you just solve for that. Okay. Typically, these are really long algebraically to do, and you're punching in a bunch of cumbersome numbers because the mass of the sun is 2 times 10 to the 30th kilograms, and these R's are huge numbers, and G is a very tiny number, but it's still long. It takes a long time to punch in your calculator. So it's a lot of work from a calculator point of view. But the actual physics of it is very simple. Okay, and that gets you, given any condition, say over here, you can figure out stuff that's happening over here just by knowing that the energy doesn't change as this thing goes around. The total energy stays the same. All right, thanks.